Now, in this second part of the liver functions, we are going to learn about more information about bile formation and secretion and ammonia handling by the liver. Other bile constituents. As noted earlier, bile also contains cholesterol and phosphatidylcholine. Cholesterol transport across the canalicular membrane is mediated, at least in part, by a heterodimer of the active transporters as participating in the efflux of cholesterol from the small intestinal epithelial cells, namely ABC5 and ABC8. Phosphatidylcholine derives from the inner leaflet of the canalicular membrane and is specifically flipped across the membrane by another ABC family transporter called multidrug resistant protein 3, MDR3. So you see MDR3 here. Furthermore, because mixed micelles composed of bile acids, phosphatidylcholine, and cholesterol are osmotically active and the tight junctions that link adjacent hepatocytes are relatively leaky, water is drawn into the canalicular lumen as well as other plasma solutes such as calcium, glucose, glutathione, amino acids, and urea at concentrations essentially approximating those in plasma. Finally, conjugated bilirubin, which is water-soluble, and a variety of additional organic anions and cations formed from endogenous metabolites and xenobiotics are secreted into bile across the apical membrane of the hepatocyte. Here you see the pathways for entry of solutes into bile. Okay, these are hepatocytes and these are tight junctions here. Active secretion to bile acids, phosphatidylcholine, conjugated bilirubin, and xenobiotics, whereas passive permeation of water, glucose, calcium, glutathione, amino acids, and urea. Bile modification in the ductules. The cholangiocytes lining the biliary ductules are specifically designed to modify the composition of bile. Useful solutes such as glucose and amino acids are reclaimed by the activity of specific transporters. Chloride ions in bile are also exchanged for bicarbonate, thus rendering the bile slightly alkaline and reducing the risk of precipitation of calcium in this way. Glutathione is broken down on the surface of cholangiocytes into its constituent amino acids by the enzyme gamma-glutamyl transpeptidase, and the products are reabsorbed. Bile is also diluted at this site in concert with ingestion of a meal in response to hormones such as secretin that increase bicarbonate secretion and stimulate the insertion of aquaporin water channels into the cholangiocyte's apical membrane. Flow of bile is thereby increased during the postprandial period when bile acids are needed to aid in assimilation of lipid. Here you see the major transport processes of cholangiocytes that secrete an alkaline-rich fluid and reclaim useful substances. Okay, this is the extracellular fluid, and this is the lumen of the bile duct. As you see, chloride, bicarbonate is secreted, and then also amino acids. Glutathione is degraded, and amino acids are present in bile. Role of gallbladder. Finally, bile enters the ducts and is conveyed toward the intestine. However, in the period between meals, outflow is blocked by constriction of the sphincter of Oddi, and thus bile is redirected to the gallbladder. The gallbladder is a muscular sac lined with high-resistance epithelial cells. During gallbladder storage, bile becomes concentrated because sodium ions are actively absorbed in exchange for protons, and bile acids as the major anions are too large to exist across the gallbladder epithelial tight junctions. However, although the concentration of bile acids can rise more than 10 times, bile remains isotonic because a single micelle acts as only one osmotically active particle. Here you see the mechanisms accounting for concentration of bile during storage in the gallbladder. So as you see, water is reabsorbed, sodium is reabsorbed, hydrogen is excreted, making the gallbladder concentrated. Any additional bile acids monomers that become available as a result of concentration are thus immediately incorporated into existing mixed micelles. This also reduces to some extent the risk that cholesterol will precipitate from bile. However, cholesterol is supersaturated in the bile of many adults, with precipitation normally being inhibited by the presence of antinucleating proteins. Prolonged storage of bile increases the chance that nucleation can occur, thus making a good case for ever skipping breakfast and perhaps explaining why gallstone disease is relatively prevalent in humans. Bile is secreted from the gallbladder in response to signals that simultaneously relax the sphincter of Otti and contract the smooth muscle that encircles the gallbladder epithelium. A critical mediator of this response is cholecystokinin. Indeed, this hormone was named for its ability to contract the gallbladder. In addition, intrinsic neural reflexes and vagal pathways, some of which themselves are stimulated by the ability of cholecystokinin to bind to vagal afferents, probably also contribute to gallbladder contractility. Here you see the mechanism of gallbladder contractility. When there is food, fat in the duodenum, it causes the stimulation of cholecystokinin from the duodenal eye cells, and then they are released into the blood circulation, and then via blood circulation, cholecystokinin arrives in gallbladder, causing contraction of it, and then sphincter of Otti is relaxed at the same time. You see here nervus vagus role and neurotransmitters taking part in contraction and relaxation of the smooth muscles. The net result is ejection of a concentrated bolus of bile into the duodenal lumen, where the constituent mixed micelles can aid in lipid uptake. Then, when no longer needed, bile acids are reclaimed and re-enter the enterohepatic circulation to begin the cycle again. However, the other components of bile are largely lost in stool, thus providing for their excretion from the body. Bilirubin formation and excretion by the liver. This is another story of the liver, the most important function of the liver, one of them. Liver is also important for excretion of bilirubin, which is a metabolite of heme that is potentially toxic to the body. Bilirubin has recently been shown to act as an antioxidant, but it also serves as a way to eliminate the excess heme released from the hemoglobin of senescent red blood cells, old red blood cells. I mean, indeed, red blood cells account for 80% of bilirubin production, with the remainder coming from additional heme-containing proteins in other tissues such as skeletal muscle and the liver itself. Bilirubin is capable of crossing the blood-brain barrier and, if present in excessive amounts, results in brain dysfunction for reasons that are not well understood. It can be fatal if left untreated. Bilirubin and its metabolites are also notable for the fact that they provide color to bile, feces, and to a lesser extent urine. By the same token, when bilirubin accumulates in the circulation as a result of liver disease, it is responsible for the common symptom of jaundice or yellowish of the skin and conjunctiva. Bilirubin is synthesized from heme by a two-stage reaction that takes place in phagocytic cells of the reticuloendothelial system, including Kupffer cells and cells in the spleen. The enzyme hemoxygenase that is present in these cells liberates iron from the heme molecule and produces the green pigment biliverdin. This biliverdin in turn can be reduced to form yellow bilirubin. Because this molecule is essentially insoluble in aqueous solutions at neutral pH, it is transported through the bloodstream bound to albumin. When this complex reaches the liver, it enters the space of this where bilirubin is selectively taken up across the basolateral membrane of hepatocytes via an OATP transporter. Here you see hem coming from hemolysis of the old red blood cells, phagocytized by macrophages in the spleen and liver also, and then it is converted to biliverdin by hemoxygenase enzyme, and then later on bilirubin. Bilirubin is taken by albumin via blood circulation. It arrives in the liver. Okay, in the liver, it's going to be conjugated with glucuronic acid, then it becomes water soluble, and then it will be excreted into the small intestine. In the microsomal component, bilirubin is then conjugated with one or two molecules of glucuronic acid to enhance its aqueous solubility. The reaction is catalyzed by UDP glucuronyl transferase enzyme. This enzyme is synthesized only slowly after birth, which explains why mild jaundice is relatively common in newborn infants. Bilirubin conjugates are then secreted into bile by a multidrug-related protein located in the canalicular membrane. Notably, the conjugated forms of bilirubin cannot be reabsorbed from the intestine, thereby ensuring that they can be excreted. However, transport of bilirubin across the hepatocyte and indeed its initial uptake from the bloodstream is relatively inefficient, so some conjugated and unconjugated bilirubin is present in plasma even under normal conditions. Both circulate around to albumin, but the conjugated form is bound more loosely and thus can enter the urine. In the colon, bilirubin conjugates are deconjugated by bacterial enzymes, whereupon the bilirubin liberated is metabolized by bacteria to yield urobilinogen, which is reabsorbed, and urobilins and stercobilins, which are excreted. Absorbed urobilinogen in turn can be taken up by hepatocytes and reconjugated, thus giving the molecule yet another chance to be excreted. Measurement of bilirubin in plasma, as well as assessment of whether it is unconjugated or conjugated, is an important tool in the evaluation of liver disease. The presence of unconjugated bilirubin, which is essentially fully albumin-bound and cannot be excreted in urine, reflects either loss of UGT or a normal temporary delay in its maturation in infants, or a sudden oversupply of heme that overwhelms the conjugation mechanism, such as occurs in transfusion reactions or in rhesus-incompatible newborn babies. Conjugated bilirubinemia, on the other hand, is characterized by the presence of bilirubin in urine, to which it imparts a dark coloration. This is indicative of genetic defects in the transporter that mediates bilirubin diglucuronide secretion into the canalicculus, or it may be due to blockage to flow of bile, perhaps caused by an obstructing gallstone. In both cases, bilirubin conjugates are formed in the liver but with no means of exit. They regurgitate back into plasma for urinary secretion. Now, finally, ammonia handling by the liver. Ammonia is a small neutral metabolite that arises from protein catabolism, and bacterial activity is highly membrane permeant. The liver is a critical contributor to the prevention of ammonia accumulation in the circulation, which is important because, like bilirubin, ammonia is toxic to the central nervous system. The liver eliminates ammonia from the body by converting it to urea via a series of enzymatic reactions known as the urea or Krebs-Henseleit circle. The liver is the only tissue in the body that can convert ammonia to urea. Here you see the urea cycle. Ammonia enters the urea cycle and forms urea, as you see here. Ammonia is derived from two major resources. Approximately 50% of it comes from uh, bacteria in colon, produced by bacterial ureases. Because the colonic lumen is normally slightly acidic, some of this ammonia is converted to ammonium ion, which renders it impermeable to the colonic epithelium and therefore allows it to be excreted in stool. However, the remainder of the ammonia generated crosses the colonic epithelium passively and is transported to the liver via the portal circulation. The other major source of ammonia, approximately 40%, is the kidney. A small amount of ammonia, about 10%, is derived from the amination of amino acids in the liver itself, biometabolic processes in muscle cells, and via release of glutamine from senescent red blood cells. The mass balance for ammonia handling in a healthy adult is presented in figure 31 to 15. As just noted, ammonia is a small, neutral molecule that readily crosses cell membranes without the benefit of a specific transporter, although some membrane proteins transport ammonia, including certain aquaporins. Here, ammonia homeostasis in health. So 25% by colonic excretion, 75% by urinary excretion. The liver for conversion of ammonia to urea. So renal production, red blood cells and muscle, they produce ammonia. Ammonium or urea is important for hypertonicity in the renal interstitium. Renal interstitium has 1200 milliosmol osmolarity. So urea helps this hyperosmolarity establishment and maintenance in the renal medulla, and this high osmolarity in the renal medulla is important to produce concentrated urine in the presence of antidiuretic hormone. Antidiuretic hormone opens the water channels so that when ultrafiltrate passing through the distal tubules and collecting ducts, water is going to be absorbed into the renal interstitium so that concentrated urine can be formed. By the way, here the ammonia Homeostasis in health, you can see ammonia formation, and then it is excreted in urea 27.5%. Ammonia is converted to urea, and then urea is excreted via urine. It provides hypertonicity in the renal medulla, as I said, and then 25% goes to the colon, then forms the ammonium ion, and it is excreted in the feces. You see here the ammonia is also absorbed via portal circulation to the liver and to the systemic circulation, and then liver converts ammonia into urea. Ammonia is causing hepatic coma. If liver does not work properly, if a liver does not remove ammonia from the blood, so in the blood ammonia concentration goes up and then can cause coma in patients with liver insufficiency. So this is called hepatic coma. Whatever the mechanism for transport, the physical-chemical properties of ammonia ensure that it is efficiently extracted from the portal and systemic circulation by hepatocytes, where it then enters the urea cycle to be converted to urea and is subsequently transported back into the systemic circulation. Urea is a small neutral molecule that is readily filtered at the glomerulus, and it is reabsorbed by the kidney tubules such that approximately 50% of the filtered urea is excreted in urine. Urea that enters the colon is either excreted or metabolized to ammonia via colonic bacteria, with the resulting ammonia being reabsorbed or excreted. If the metabolic capacity of the liver is compromised acutely, coma and death can rapidly ensue. In chronic liver disease, patients may experience a gradual decline in mental function that reflects the action of both ammonia and other toxins that cannot be cleared by the liver in a condition known as hepatic encephalopathy. The development of confusion, dementia, and eventually coma in a patient with liver disease is evidence of significant progression, and these symptoms can prove fatal if left untreated. Now, clinical assessment of liver function. Given the importance of the liver for homeostasis, tests of liver function are a mainstay of clinical diagnosis. Such tests have several goals. First, to assess whether hepatocytes have been injured or are dysfunctional. Second, to determine whether bile excretion has been interrupted. And third, to evaluate whether cholangiocytes have been injured or are dysfunctional. Liver function tests are also used to monitor responses to therapy or rejection reactions after liver transplantation. However, not all such tests measure function directly. Nevertheless, liver function tests are discussed briefly because of their link to hepatic physiology. By the way, uh, when a lobe of the liver is taken to transplant to a patient with liver insufficiency, uh, the donor's liver will grow up and then will form the lobe taking away, and then the growing of the liver will stop when the lobe arrives in the previous size. It's really interesting. Tests of hepatocyte injury rely on markers that are specific for this cell type. When hepatocytes are killed by necrotic responses to inflammation or infection, for example, they release enzymes including alanine aminotransferase and aspartate aminotransferase. These enzymes, which are essential to interconvert amino acids, are easily measured in serum and indicate hepatocyte injury, although aspartate transaminase or AST may also be released after injury to other tissues, including heart. Two other tests are markers of injury to the biliary system. Alkaline phosphatase is expressed in the canalicular membrane, and elevations of this enzyme is in plasma suggest localized obstruction to bile flow. Similarly, increased levels of gamma-glutamyl transpeptidase or GGT are seen when there is damage to cholangiocytes. Measurement of bilirubin in the circulation or in urine also provides an insight into the liver function. In addition, measurement of any of the other characteristic secreted products of the liver can be used to diagnose liver disease. Clinically, the most common tests are measurements of serum albumin and a blood clotting parameter, the prothrombin time. If results of these tests are abnormal when considered together with other aspects of the clinical picture, a diagnosis of liver disease may be established. Now, finally, the key concepts. First, vital functions of the liver include carbohydrate, lipid, and protein metabolism and synthesis, detoxification of unwanted substances, and excretion of circulating substances that are lipid soluble and carried in bloodstream bound to albumin. The liver also synthesizes the majority of plasma proteins, including albumin. And the second, liver function depends on its unique anatomy, its constituent cell types, especially hepatocytes, and the unusual arrangement of its blood supply, uh, portal circulation. And the third, substances are excreted from the liver in bile. Bile flow is driven by the presence of bile acids, which are amphipathic end products of cholesterol metabolism that are produced by hepatocytes. Bile acids circulate between the liver and intestine to conserve their mass, and water-insoluble metabolites, such as cholesterol, are carried in bile in the form of mixed micelles. And the fourth, bile is stored in the gallbladder between meals, where it is concentrated and released when hormonal and neural signals simultaneously contract the gallbladder and relax the sphincter of Oddi. And the fifth, liver is critical for disposing of certain substances that would be toxic if allowed to accumulate in the bloodstream, including bilirubin and ammonia. This is the end of the second part of the liver functions. Thank you very much for listening.